Okay. So good morning to all and welcome to lecture number 13. So today we'll talk about scale space approach, remaining part of the scale space approach, particularly how to select the scale in the scale space approach. So that part is left from yesterday's talk. And then after that, we'll talk about how to detect the edges in multispectral images. Okay. So yesterday we talked about this scale space approach, and then why scale space multiple scale representation is important in images, and then what are the different approaches, like for example wavelength based approach is one of the technique for multiple scale representation of the image. Then Laplacian of Gaussian is there, and then pyramidal structure and so on. So we have seen the pyramidal structure, as well as yesterday we talked about something about wavelet based approach also, and then after that I talked about the Laplacian of Gaussian, and so up to that point we have covered in our yesterday's talk. Now we'll continue that one. So here this was the yesterday we have seen that, like for example, this is your original image, and then after doing the Gaussian filtering and decimation by 2, row wise and column wise you got this image. After that, what you do, you can do the upsampling of that image, and then you get this. So definitely what happens here, when you take the Gaussian filtering of this image, so low pass component will be passed and the high pass will be removed in some extent, and so this is the low pass version of this one. And then after decimating it row wise and column wise, you get the image like this. Again, to obtain the high pass component, what you are doing here, you are just doing the upsampling of this one, and you got this image. Now, what is the difference between this image and this image? See that this is the image of same size, that is similarity. Only thing is that this is the Gaussian version of this image. Now, Gaussian version means low pass filtered image, so high pass component is not there, which is present here. So what we have done to detect the high pass component, so just we have subtracted this image from this image. So here subtraction option is there, and then you got the high pass component, that is the edges which are detected in the image. So this is the Laplacian of this one, right? Again, what is done next level, so with G2 filter, this image is this one Gaussian filtered, and again decimation, same process is done here, and then you got the half size image here, right? Again, same process, like for example upsampling and then reconstruction of the image, and then this image and this reconstructed, this is the original image and this reconstructed image, you are finding the Laplacian of that one, that is nothing but the high pass component, right? So same procedure is repeated, and then you get the low pass as well as high pass representation of the image, and in high pass you get the edges detected. So with various scale you get the edges detected in the this one, so in the of the image and so on. So like that way, at multiple scale you can detect the edges. Now question is that how to select the scale, right? So which scale is suitable for which kind of component in the image and so on. Like for example here, suppose this is your image of circular object having the radius equal to r, right? So when this when this circular object will be detected by the Gaussian filter, so see the Laplacian of that one will take the Gaussian as well as Laplacian of that one. So at what scale does the Laplacian achieve a maximum response for a binary circle of the radius r? So this is the binary circle. Binary, why? Because you have this white background and then this is the black object, right? So that's why it is called the binary image. So only two scales, levels are there. or two shades are there. So, and this object is having radius equal to r. Now, when this object will be detected, with which scale it will be detected, that is what we have to basically detect, right? Now here, see that the experiment was conducted, and then you know that the 2D Laplacian Gaussian is given by this equation, and you know that x and y are the coordinates of the special coordinates, and then sigma is nothing but the standard deviation. Now this sigma value is such that, okay, for the Gaussian kernel, this sigma value will be such that it will detect this kind of circle when the sigma is equal to r by root 2. See that if the sigma is equal to r by root 2, it will give the maximum response at that for that circle, and so on. So see, that means for detecting this circle very clearly, okay, your sigma value of that Gaussian function should be equal to r by 2. If a small circle is there, then again we have to, you should know that this r by 2, and then or this, you should know the radius of that circle, and then sigma value of that will be equal to r by 2, which will detect the small circles, and so on. So like that way you can detect the this one, the objects with multiple scale. Means when you are changing, see, we are changing the value of sigma, so changing value of sigma is nothing but changing the scale. So by changing the scale, you are detecting the different objects, and so on. Now when this object will be detected, if the sigma value is equal to r by 2, where r is nothing but the radius of that circle. So see that here, the Laplacian Gaussian from Blob detection, like for example, there are so many circular objects or flowers are there, and so on. So because flowers are also circular kind of thing, and you know that the Laplacian of Gaussian is given by this equation, partial derivative with respect to x, okay, double derivative with respect to x and double derivative with respect to y of Gaussian function, right? So you get the filters, like for example, by changing the sigma value, you get the filter, different filter size. Now this filter will definitely detect the small this one objects or small circular objects. This will detect bigger than that one, and so on. So definitely this kind of circular objects will be detected with a small value of sigma. Then mid size will be detected by like this, and the large size will be detected like this. So in this way, you get the at various scales. Suppose, for example, at this scale, at this scale you'll detect the small objects. At this scale, you'll detect the medium object, and at this scale, you'll detect the large object, and so on. So, like for example, this is the circular object, and then we define this characteristic scale as the scale that produces a peak of log response. So this it will detect this object and having the peak like this. So that when it will detect the value object. This will detect the object when sigma is equal to r by 2, where r is nothing but the radius of this circular object. So this was proposed by Lindenberg in 1998 for detection of feature detection with automatic scale selection. This is the paper which is published in International Journal of Computer Vision in 1998. And then this can be extended for detecting the blobs in the image or various circular objects in the image. So definitely circular objects may be small size circular circles or medium size circles or big size circles. So definitely these will be detected at various scale by changing the sigma value. So at that time, what you have to do, you have to convolve the image with the scale normalized LOZ at several scales. So at scale 1, that is sigma 1, you get the Laplacian Gaussian operator. Then at sigma 2, you get another Laplacian Gaussian operator. So every time you have to convolve that LOZ operator with the image, and you will get particular output. Like for example, at scale 1, you get the output like this. At scale 2, you get the output like this. At scale 3, you get the output like this. And then at change, as you go on increasing the sigma value or increasing the value of scale, then you are going to detect the largest size object and so on. So find the maxima of squared LOZ response in the scale space and so on. Like for example, this is the image So this well-known sunflowers are there, but you know that okay, all those sunflowers are same size, but what happens basically, the sunflowers which are very close, they will look bigger in size, whereas the sunflower which are at far end, they will look like as a small sunflowers. But in actual, they are, see why? Because scale is changed there and so on, right? The distance is changed from viewing object, okay, viewing person and so on. There are so many circular objects in this image. Now for detecting this one, we have to use, for detecting all those circular objects, we have to use multiple scale Laplacian Gaussian. So definitely, if scale is small, it will detect the small object, and if scale is large, it will detect the large object and so on. So like that way, for a smaller scale, it will detect the smaller object very prominently, whereas larger objects are not detected prominently, but smaller objects are detected prominently, right? So because smaller objects are at the back side, where larger objects are there at the front side. Okay, as scale goes on increasing, it will try to detect the medium-sized object, right? Whereas large size and small size objects are okay, less detected. As scale go on increasing, again it will detect the large size object, whereas small size objects are detected faintly or they are not detected and so on. Means at multiple scale you are going to detect the multiple object, and then when you combine all those things together, you are going to detect all those objects which are present in the image, right? So local maximum in space and scale is okay in the reduced image and so on. So like that way you are going to detect this is scale is increased, sigma is 9.8 here, so it will detect the large size object. Earlier sigma size was less, so it was detecting the small size object and so on. So like that way at multiple scale you are going to detect the multiple objects and so on, right? So I hope that this is very clear how to select. So for selection of the scale, what you have to do, if the object size or radius is around r, then scale sigma value should be equal to r by root 2. So this is the experimental done by the researcher to decide the scale in 1998, which I have shown you in the paper. So that way. You can also obtain the scale invariant features of this okay, by using what you can obtain the images with multiple scales, and then you can normalize the things, and then you can get the scale invariant properties and so on. So the interest points of local maxima in both position and scale can be achieved. Just what you have to do, you have to obtain the images with multiple scales, and then you have to normalize the things, and then combine the thing, you'll get the scale invariant property in that. I hope that now this is very clear how to select the scales in the multi-scale, this one, scale space approach and so on, right? Now the second part of this lecture is and this is the last part of this chapter, that is how to detect the edges in multispectral images. Okay. Now, you know that images we have studied are like as a grayscale image or binary image or a color image and so on, right? So that images are called the pan image basically, right? Color image is also called as the multispectral image because it has a multiple bands like as R band or R channel, G channel, and P or CP channel, and so on. So in the grayscale image, you have only one plane. In the multiple spectral, you have several planes. Image is represented with several planes. Like for example, in case of this one, color image is represented with R plane, Z plane, and B plane, right? So RGB plane will form the color image. In case of satellite image, suppose for example, there are 7 bands, and then this satellite image, satellite camera will capture the image of same region with 7 different lambda values. So with lambda 1 you get one image, then with lambda 2 you get another image, then lambda 3 third image, lambda 4 fourth image. So like that way, lambda 7, seventh image. So of the same region, you got the 7 different images, and then these images are just like as a stack of the images, and so one pixel will be represented in that case as a vector. So sometimes it is also called as a vector valued image, right? Whereas in case of grayscale image or binary image, it is not a vector valued image; it's a parametric image, right? And but when images are represented with multiple wavelength, okay, multiple wavelength, see that in case of RGB image also, your visible spectrum is ranging from 400 nanometer to 700 nanometer. So around the wavelength of blue channel is around 440 nanometer, then G channel is around this one 540 nanometer, and then this one red channel is around 650 nanometer. So you are representing the color image with multiple wavelength, right? So similarly, in the case of satellite images also, it is represented with multiple wavelengths, so with the different bands of the satellite images. So normally it may satellite camera may have this one images from 7 band to 12 band and so on, so like that way. So if it is 7 band, then you'll get the seven images with first image as a lambda 1 image, second lambda 2, and seventh will be lambda 7. So similarly for 12 band, it will be 1 to 12 images will be there. So such images are called as the multispectral images. But we'll see the difference between multispectral image and what is the difference between multispectral image and hyperspectral image. So before that, the edges in multispectral images, the main difference between the multispectral and the hyperspectral is the number of bands and how narrow the bands are. See that. Okay, so see that here, in a case of multispectral image, the number of bands are ranging from 3 to 10 bands. Okay, number of bands are limited. Like for example, you have this visible spectrum, which is ranging from 400 to 700 nanometers. So there are 3 bands, like as blue channel, green channel, and this one. And again, you have infrared band, and then this one. So if it is ranging from this one, a microwave to visible spectrum, then you may have, suppose for example, 7 band to 10 bands or something like that. So in multiple spectral or multispectral imagery, generally refers to 3 to 12 bands, and each band has the descriptive title. Whereas in hyperspectral images, okay, in hyperspectral images, it consists of much narrower bands. See, these are the wider bands, but these are the narrower bands in hyperspectral images. And then these number of bands may be hundreds or thousands of bands may be there. See that in case of hyperspectral, see number of bands are hundreds or thousands of bands, whereas in case of multispectral images, number of bands are limited to 10 to or 3 to 12 or like that. Up to 10 bands. And these bands are wider bands, whereas hyperspectral bands are very narrow bands are there, right? So for example, here multispectral, the channels below include red, green, blue, and near infrared, and then shortwave infrared, and so on. So these are the wide band channels basically, and which comes under like as a multispectral. Whereas in case of hyperspectral, hundreds of narrow bands are there, which may be in the infrared, which may be in the visible. See that in case of visible, here there are only 3 bands, but here in visible spectrum itself they have taken like as 50 bands or something like that. So number of bands are more in this case. So definitely if number of bands are more, you'll find more details in the hyperspectral images, whereas you'll find less details in the multispectral image. Another thing is that, see, definitely when you are getting more information, memory required to store this will be also more as compared to this one, right? And at every band you get the different information because your lambda value is changed, wavelength is changed, so frequency will be changed, and if frequency is changed, definitely the objects which may be visible in one band may not be visible in another band, and so on. So I hope that this is very clear to you, the difference between the multispectral images and hyperspectral images. So Just to summarize it, multispectral images contains a number of bands less, 3 to 10 to 12, or here number of bands are 100 to thousands of bands are there. And then in multispectral, second one is that bands are wider band, where here bands are narrower band, and the size of each band is 10 to 12 nanometer. Okay, and here see that within 300 to 400, 300 to 700 nanometer, how many bands are there? Basically, 3 bands are there. It means the size of each band is around 100 nanometer, whereas here it is 10 nanometer. So within one band here there will be 10 bands or like that. Okay, so this is the difference. And another thing is that this gives more details, whereas it will give less details. Fourth thing is that memory required to store will be more in case of hyperspectral images, whereas memory required to store will be less as compared to hyperspectral images, because number of bands are less here, and so on. Then an example of multispectral sensor is Landsat 8, for example, and also Landsat 8 produces 11 images, that 11 channels are there, and the spectral resolution is less than that of the hyperspectral images resolution, as I said. Whereas example of this hyperspectral images is that in 2000 NASA launched the EO-1 satellite, which carried the hyperspectral sensor whose name was Hyperion. And in fact, the Hyperion imaging spectrometer was the first hyperspectral sensor from space, and Hyperion produces 30-meter resolution images in the 242 spectral bands. Okay, and this one, which was ranging from 0.4 to 2.5 micrometer and so on, right? So hyperspectral images gives better spectral resolution as compared to multispectral images. But at the same time, as I told you that memory required to store this will be more in this case as compared to this. So this is very clear now, the difference between the hyperspectral imaging and multispectral imaging. Now we'll see how to detect the edges in the multispectral images. Can we extend the edge detection techniques which are studied for a grayscale image or binary image? Can we extend this idea to the multispectral image for edge detection, or there can be a different approach for detecting the edges and so on? So we'll see 3 methods which are there given in the standard book of your Milan Sunka. So first method to detect the edges in multispectral image is that what you can do. First method is very simple, that detect the edges in the individual image spectral component by using local gradient operator. Now, which are the local gradient operator? Okay, so you know that the local gradient operators are like, as the Sobel operator is there, Privet operator is there, Krish operator is there, Robert operator is there. So for example, you have this 7-band images is there. So consider only one band. So one band will have the intensities from 0 to 255 if each pixel is represented in that band with a 8 bit. So it will be having the range from 0 to 255. Consider that as an individual image and apply those gradient operator on individual plane, right? Then again on second plane, third plane, fourth plane, up to 7th plane, right? Like that. So apply all those edge detectors which we have studied for grayscale imaging or for this one, your binary images and so on. You can apply for the same thing. Or even in the color image also you can do. Like for example, you can separate out the channel as a green channel, and then blue channel, and then red channel, and then apply those local gradient operators in each channel separately. And then finally, what you have to do, once you have done this one, second step, you have to do combine the individual images of edges to get the resulting image. So once you have detected the edges in individual planes, so just add those things, combine those things with the value corresponding to the edge magnitude and direction being in the maximal edge value from all the spectral component. So either you can add or you can take the maximal value from every spectral component, and then finally you can have the age detected image in the multispectral. So this is very simple approach which can be used for detecting the ages in the multispectral image, right? I hope that this is very clear to you. Okay. Now the second method for detecting the ages in multispectral images is that instead of using this gradient operator and applying those gradient operator on individual plane, so what is done basically here, use the brightness difference of the same pixel in two different spectral component. Like for example, you have spectral component, also, like for example, first spectral component or first band is given by Z1, R comma C. R is nothing but the row and C is nothing but the column. Z1 image, G1 is first plane, then Z2 is second plane, Z3 is third plane, Z7 is your seventh plane. So what you can do here, you can take the difference between the consecutive, means between G2 and G1, okay, or Z3 and Z2, and so on, or G7 and G6, and so on. So use the difference, the brightness difference of the same pixel in the two different spectral component, and then find out this brightness difference. So this is nothing but the brightness difference of this nth component and nth plane and nth plane of same row and column or same pixel, and so on. And then okay, so this is one technique. You can extend that one up to whatever you have the planes. Like for example, you got the difference between first and second one, then this whatever the value you get, again you subtract it from the third one, again you get the this one again, so like that way. So you'll get the finally resultant image, which is just like as a age detected image, and so on. So different techniques from the all spectral component. Sometimes it may happen that instead of difference, the ratio instead of difference can be also used. See, only difference is also not used, but sometimes we can use the ratio between the ZM RC. See, here we have taken the difference. Another technique for detecting the ages is also to use the this one ratio. So ZM RC by GNRC. So you know that GM is one spectral component of that multispectral image, and GN is another spectral component. So you are taking just ratio of that one. So that is also another technique for detecting the ages in multispectral. So very simple techniques are there, which are reported in the literature or in the standard books. Now, the third technique, okay, which is used for multispectral images, and this is widely used because its response is, or its result is really good as compared to the previous two methods. So what they have done, like for example, you have the image of 7-band images there, like first band, second band, third band, up to 7-band images there. So instead of, see, in the first this one, what we have done in the first method, we have treated every band separately by applying the standard gradient operator, and then we detect the age for first band, then second band, up to 7th band, right? So that was our first method. Second method was that we were taking just difference or ratio of the pixel between the adjacent bands. So that was the technique for second age detection technique in multispectral images. Now in this third technique, what you have done, like for example, you have this 7-band images there. So consider a group of pixel, like volumetric image of, like for example, if you are considering a in robot operator, what you are doing, you have the operator size as a 2x2 or 3x3 and so on. So you can consider a 2x2 volume of every from every plane or every band, and then see, to create the multispectral age detector, which uses the brightness information from all n spectral bands, the neighborhood used has the size 2x2 by n. So number of rows and number of columns are 2, and how many spectral components? N spectral components are there. So you get the volumetric image of size 2x2 by n, where 2x2 is the neighborhood similar to that of the Roberts gradient, right? So in that way you are selecting this one. Now what you are doing here, let f tilde Ij denote the arithmetic mean of the brightness corresponding to the pixel with the same coordinates I comma j in all n spectral component image. So what you're doing here, you're finding the f tilde I comma j, which denotes the arithmetic mean of the brightness corresponding to the pixel with the same coordinate I comma j. So you have considered 2 by 2 and then n spectral component, and then you are taking the arithmetic mean of the brightness of that one. So like for example, if value of n is 7, so 2 by 2 by 7, now you have the first pixel, and then how many corresponding planes are there? 7 planes are there. So you are taking the arithmetic mean of that intensity value, and then it will be represented like that. Okay, so f tilde ij denotes the arithmetic mean of the brightness corresponding to the pixel with the same coordinates I comma j in all n spectral component image, and fr be the brightness of rth spectral component. Okay, fr be the rth spectral component. Now if you know the f tilde and fr, from that you can calculate the see what is that? F tilde is the arithmetic mean of brightness of corresponding pixel with same coordinates I comma j in L spectral component. And what is fr? Fr is the brightness of rth spectral component. Now if you know this fr and f tilde I comma j, then from that one the edge detector results in a pixel I comma j is given as the minimum of this following expression. What is this one? So you are doing the summation of FRI of Ij. What is this FR of Ij? Is the brightness of rth spectral component at location I comma j. You are finding the edge at a location I comma j. See, you are finding the edge at I comma j. So for that, what you are doing? You are considering the brightness of rth spectral component. So this rth spectral component, and then you are subtracting what? This one basically mean this one mean value, arithmetic mean value from that one. So f of ij, and then multiplied with fr of I plus 1 j plus 1 minus tilde or bar, we can say I plus 1 j plus 1. So with implementation of this one, and divided by same thing, like for example a summation under root summation r equal to 1 to n fr of ij like this, and then minus this one, just square of it. Again same thing, same pixel coordinates are there like this above here also, and square of this one. So you are dividing this one, so you got this value, and also you got the another one see that here it is fr I comma j, here it is fr I plus 1 j. So you are considering the different pixels here, 2 by 2. And then from these two values you are selecting the minimum of this one. So whatever the minimum value you get, so that will be the corresponding pixel value, and then that will be detected, that will give you the edge value from all those R spectral components. So this multispectral edge detector, if you apply like for example considering 2 by 2 of all spectral component, like then again next 2 by 2, so you have to do row wise and column wise till you cover the entire image, and then finally you will get the multispectral edge detector image, and this gives the good result as compared to the previous two methods on remotely sensed images or so on. So in this way you can extend or you can find the edges in multispectral image, as well as you can find the edges in the grayscale image or binary image and so on. So edge detection is one of the important part in the computer vision, and this finishes our chapter number 2, and then from next lecture we'll start chapter number 3, that is nothing but the mid-level computer vision part. So from tomorrow we'll start. So thank you very much. We'll stop here.